Hello everyone, in this video I'd like to discuss how can we do the testing for the bilinear transform for the Z transform convert from the S domain transfer function into Z domain transform, ultimately convert to difference equation. And in the topic 2 and 3, I discussed how can we convert a first order transfer function into Z domain Z transform. At the time I discussed how can we involve the zero holder. And in the previous video, I introduced how can we determine a second order underdamped transfer function. And using the same idea, then the next step after determined a second order transfer function, we will do the same thing using the zero holder concept and convert to the Z transform. Then the basic method, if we do a quick review, while we are doing the first order transfer function, so we will involve the zero holder and using this equation, this method to ultimately convert to this style. However, you will see manually derive this equation is super complicated. This is the first order, then you need to do this derive and ultimately got this result. The basic idea is originally you have the first order transfer function. Then using this equation, we manually derive the equation, convert to the Z domain, this style, and then convert this Z transfer equation into the difference equation like this. This is the first order, but people will ask, if we have the second order transfer function like this, how can we use this equation and manually derive into the Z transform? I would say this manual derive is a super challenge. This derive came from the couple years ago. I manually derived this. And recently, I found this is my note. It derived where this method derived this second order underdamped transfer function ultimately got this result. This is a difference equation, but I would say this is horrible. This is the second order underdamped transfer function, but in case one day you have another style of S domain, how can we convert using this way? It's super complicated. Then this come up a more practice way. Basically, in the theory area, we called bilinear transform by using this Tustin transform. This basic idea is using the approximate method. So any control theory book, you can search the bilinear transform or you can search the Tustin transform. Then you can find the detailed explanation how that came from and how can we implement this method. I will not discuss the detail how that's come from, but more importantly, I'd like to discuss this concept, how can we use this? And very important page, you do not need to read any book, but very important page, you better go to the Wikipedia. And if you search this bilinear transform and you scroll down, basically this using the discrete time approximation idea. And then using this method, then the S can be substituted by this. K, the denominator is a Z plus 1 and the numerator is a Z minus 1, where K is equal to this. T, 2 over T. T is your sample time. T is a sample time to run your difference equation. So here, this is the entire equation. Then if you have one S domain transfer function, you can substitute this equation into this S domain transfer function. Then you can see your equation will be converted to the Z domain. This method, so-called Tustin transform. Then if you scroll down, I super like this Wikipedia, this page, then it comes with some example, and more importantly, I think is very useful is here, transform for general first order continuous time filter. This is the first order transfer function. And then this is the second order transfer function. And this is the common format here. So while we are talking about the first order or second order transfer function, the denominator, it doesn't have the S at the denominator. But this format is a very common, is very general. So in our case, while we are talking about the first order or second order, if your denominator doesn't have S, then that means that B0 is a 0, right? Is a 0. Or here, the B0 is a 0 and the B1 is a 0. Actually, it's easy to do the conversion. And you will see if you have this first order transfer function here, then basically your difference equation, you can directly use this format here. Then you can substitute all the parameters from your S domain, directly use them, directly calculate this ratio here. And same idea for the second order transfer function. This is the common style here. And then for the difference equation, you can use this. So as we can see, this is the K, this is the current time, this is the previous of the input, and this is the output, And take care, this is the K minus 1 and the K minus 2. This is the previous sample time, this is the 2 times of the previous time, okay? Then you can use the B0, B1, A0, A1, A2, B2, then you can calculate, this is the one solid value, K equal to 2 over your sample time. For example, if your sample time is 0.1, 100 milliseconds, then the K is equal to 20, right? Then you can calculate. This is the one constant value here once you have a transfer function, as long as your transfer function determined. Then let's do a summary here. Basically, in the engineering world, while we are doing this transform, the Z transform, we can use the Tustin transformation. Then we can substitute this equation into your S domain. Then your equation will convert to directly into this format, this difference equation, this format. This is the first order, and this is the second order. Just to take care of one thing, while using the Tustin transformation, your sample time, this is the sample time, okay? Your sample time will be nice less than 1 second. So if your sample time higher than this, all those parameter approximation won't be accurate enough. Typically, I would recommend while using the computer or embedded system or PLC to implement this transform, I would recommend your TS will be nice less than 200 milliseconds. Typically, I will use 100 milliseconds. That means 0.1 seconds. Take care, your sample time must be as shorter as possible. We'll see when you pick the sample time here, all those K will be changed, okay? Because K come from this calculation. Okay, they all here. So typically the K is equal to 2 over 0.1 is equal to 20 if the sample time you are picking the 0.1 second. Take care these requirements here while using the Tustin transformation. And the detail of this equation, I highly recommend you can read the detail of this Wikipedia page. And if you like to learn more, then I highly recommend you can read the control books, read the details of the theory, and you can search the bilinear transformation, or especially for the Tustin transformation, this method to look at the detail. I like to use this to do a demonstration for here. If I use the one equation I introduced before while we're talking about the low-pass filter, and while we're using the T sample time is 100 milliseconds, basically 0.1 second as our sample time, then the result is equal to 0.88 y, this is K minus 1 plus 0.12 x K minus 1. If you remember, this value is not super accurate, but roughly the value was like this. If you recall from the previous video while I'm talking about the low-pass filter. Then using this concept, using this method here, let's see. So while the GS equal to this, let's see, then the B0 is equal to 0, and the B1 equal to 1.25, right? And A0 equal to 1, and A1 equal to 1.25, right? So this is come from here. This transfer function is this, right? Then let's calculate if we can get a similar the difference equation. Okay, so let's firstly calculate this. Let's call this the A equal to the B0 times K plus B1, and A0 K plus A1, right? Equal. So where k equal to what? K is equal to the 2 over Ts. So here in this case, Ts is 0.1. So the k equal to 20, right? So that means here the B0 is equal to 0. Then the B1 is 1.25. So A0 is equal to 1. So this is the equal to 20 plus A 1.25. Then this equal to 1.25, 21.25. Okay? Then let's calculate about this area. This is called B. So B is equal to minus B0K plus B1, A0K plus A1. Okay? Again, B0 is 0, so this is 0 plus B1, 1.25. And the denominator, they are the same, so this is 21.25. Okay? Then C is equal to this area. This is the minus and the minus A0K plus A1 and the denominator A0K plus A1. Again, denominator, they are the same, so 21.25. So nominator, let's see, this is the minus, okay? Then this area is equal to minus 20 plus the A1. A1 is 1.25. So this result is equal to 21.25, and this is the 18.75. So 18.75 equal to what? Okay, let's do this calculation. So 18.75 derive 21.25. So we will see the result 0.88. So almost the same like before. So this result equal to 0.88, right? 25. And then this area equal to what? So let's calculate. So 1.25 over 21.25 is equal to 0.588. Okay, 0.588. Then I'm temporarily write down here 0.0588. Okay, 88. Okay, I wrote here. Then we will see the difference equation will become yk. We will still use the k here, and xn. So let's firstly write the y. So y is equal to 0.88. This is the y k minus 1, right? Plus, then this time this equation we have a 2x here. So one is xk, the current k. The current k is equal to the current k. This ratio equal to 0.0588. And the next one is xk minus 1. And this is a b, right? This b here is 0.0588. Okay? Then we will compare these two equations. So actually this area we will see. This is the k time. This is k minus time. So actually these two areas, if we plus together, you will see. This is almost, if we times 2. This is almost like a 0.12. 0.12. This is the x. This is the x value. We will see this is almost the same like this. And again, so this equation, this comes from the testing, the approximation. So this parameter will be a little bit different with the original derived this method. But we will see the parameter, they almost the same. The format may change a little bit, but the parameter, they almost the same. So this is how can we calculate those parameters for those. Again, once you have this format, you calculate all those ratios for the input and output. Then you can get this ABC, then you can calculate this difference equation from the first order system. Same idea, once you have all those parameters, you can use this way to convert one second order transfer function into the difference equation. Then once you have the difference equation, you can use the similar way I introduced before, how to program into the PLC to implement this. Okay, this is the Tustin transform. Till here, maybe people will still think, okay, this is still complicated. Is there some easy way we can directly calculate this? The answer is yes. We have MATLAB, right? The only thing the MATLAB cannot do is derive the equation. So it cannot figure out how this S domain transfer function convert to this style. It cannot do that. But once we have one transfer function, S domain transfer function, we can use the c2d and then type in the ZOH, involve the zero holder, and tell the system the sample time is 0.1 second. Then we can use the MATLAB convert to Z domain transfer function. And then once we have the Z domain transfer function, we can easily get a difference equation, right? Then let me demonstrate. Firstly, I will still use this example. If we have one S domain first order transfer function, let's see if MATLAB can convert to this equation. Okay, so let's go there. Okay, MATLAB is here. Then firstly, let's create, this is the first order transfer function. That's equal to a transfer function and the denominator equal to 1.25. Okay, and denominator, this is the 1.25. Okay, we'll see this transfer function is exactly the same. Then once we convert to the Z domain and involve the zero holder, so the command will use c2d. Okay, then firstly write down the transfer function we will have. And then this is the TS. TS we will use 0.1 second. 0.1 second. And don't forget write down this ZOH. So we will use the zero holder. And this is the Z domain transfer function. And this is the sample time of the equation. Okay, let's do this convert. So we will see this parameter, they are the same. Once we have this Z domain equation, we will convert it into the difference equation. It is very easy. Please follow me. So here that means yz over xz, that equal to this 0.1175 and z minus 0.8825, right? If we times z minus 1 for the denominator and the numerator, then this equation will become z minus 0.8825 times z minus 1 yz equal 0.1175 xz times z minus 1. Then when we convert to k, so this is the yk, and this will change to 0.8825. This is the yk minus 1. And this area becomes 0.1175 k minus 1. Then if we convert this into the right side, then we will see this equation will be 0.8825 yk minus 1 plus 0.1175 x k minus 1. This is how can we convert a Z domain transfer function into the difference equation. We will see once we have this Z transform, then we can very easily get this difference equation. Then using this idea, we'll do the same thing for the second order transfer function. Okay, if you recall, while we are talking about how can we determine a second order transfer function, we were using this transfer function as the example. Then using this case, I will use MATLAB to convert. Again, the sample time is 0.1 second. Okay, here this system is a system 2 equal to the transfer function, and denominator is a 5 multiply 9, and denominator equal to s square and 2 and 9. Okay, we will see this is second order underdamped transfer function. They are the same. Then using this way, the same. Okay, so here I can write this. TS sample time is equal to 0.1. Okay, And then we will use c2d. This time system is system 2. Okay, and then the TS sample time. And again, we will use the zero holder for this convert. Okay, so we will see after this convert, this is the Z domain transfer function. Okay, same thing. So y, z, x, z equal 2187. Okay, so this is the Z transfer function from MATLAB. And we will multiply Z minus 2 power. Okay, then this equation become 2, okay, y, z, okay, then minus 1.738, so y, z multiply z minus 1, and plus 0.8187, so y, z minus 2 equal to 0.2092 x z minus 1 and plus 0.1956, so x z minus 2. Then if we convert to the k, the difference equation, this become to yk minus 1.738. This is the y k minus 1, right? Plus 0.8187. This is the y k minus 2 equal to 0.2092. This is the x, so k minus 1, right? This is the minus 1, and plus 0.1956. So this is the x, k minus 2. Okay, then once we convert this to the right side, then we will get an equation, yk difference equation, right? So we will see, using the MATLAB, using this command, we can easily get one Z transform using the zero holder concept, and the TS, it is here. Once you defined your TS, then the MATLAB can directly calculate this out. However, how those parameters came from, the MATLAB will now tell you. That means the limitation for using the MATLAB, you have to define your transfer function at first. You have to define this transfer function at first. Then once you have this transfer function, everything can be calculated by using the MATLAB. Then back to the topic I introduced before. Using this way, using the testing, all those parameters, you exactly know how they come from. And you can program all those calculations. You can set all those parameters A0, B0, A1, B1 from your HMI or from any other the input. And then you can directly calculate this entire equation, this difference equation. This is the variable style, but MATLAB, you have to solidly define your transfer function. Okay, this is basically two ways. In the practice, I saw both ways to convert one transfer function into the Z domain, into the difference equation. I saw both ways. And again, these testing transform are very important and a common way to convert one S domain transfer function into the difference equation style. Just don't forget, while we're using this testing transform, your TS, your sample time, must be very short. Typically, I would recommend your sample time will be less than 200 milliseconds. In theory, the sample time basically should less than 1 second. To make sure this approximation to accurately approximate to your transfer function parameter, I would recommend decrease the sample time. So to balance the computer, your PLC workload, I would say 100 milliseconds will be a proper value I would recommend. So in every cases in this video, I was using 100 milliseconds, 0.1 second as my sample time. So keep in mind, once you defined your sample time, then this K, take care here, the K doesn't mean the gain of your transfer function. It's just one ratio here. So this K will be a solid value. For this case, if your sample time is 0.1, then this K here is a 20. It's a constant value. Then substitute this k into all those parameters here. You can calculate all those parameters. Okay? So this is the topic in this video. How can we use the Tustin or using MATLAB to convert one transfer function into the difference equation. Thank you for watching.
Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.